All right, today we are going to really dive into some more Chapter 2 stuff with our polynomial and rational functions. We are in Section 2, which is polynomial functions of a higher degree. So let's talk about the definition of a polynomial function. If n is a non-negative integer and a sub n minus 1, just saying a bunch of different numbers, are real numbers, and the first one's not 0, then a sub n x to the n plus a sub n minus 1, x to the n minus 1, on and on and on, is a polynomial function of x with degree n. So basically what this says is you have real number coefficients and x to positive whole number powers, then it's a polynomial, all those added and subtracted to each other. The degree is n, that is your biggest exponent. Graphs of polynomial functions are always continuous. There are no breaks or jumps. And there are smooth, rounded turns. There are no sharp, pointed turns. So continuous means that's a no-no. And smooth, rounded turns means that corner right there is also a no-no. No polynomial will look like that. So graphs of polynomial functions. This one here is a polynomial. It is smooth, rounded corners. This one is not because there's a gap in it. Down here, this one is a polynomial. It's got smooth, rounded corners. This one is not the absolute value of x because there's a sharp turn. The simplest graphs of polynomials are like your parabola and your cubic-looking function. They are monomials with a coefficient of 1, like x squared, x to the third power, x to the fourth power, x to the fifth power, those single polynomials. But the rest are a little more complicated, and we'll talk about the leading coefficient test. So whether the graph of a polynomial eventually rises or falls can be determined by the function's degree, whether it's even or odd, and its leading coefficient. So remember, the degree is the biggest exponent. And the leading coefficient is the coefficient on that one. But when we write in for standard form, it's the first coefficient in standard form. So if our degree is odd, so the biggest exponent is an odd number, depending if the leading coefficient is positive or negative, tells us what our graph does. If the leading coefficient is positive, our graph is going to follow the basic shape of your cubic function, which means the left side goes down, the middle does whatever I want, and the right side goes up. If the leading coefficient is negative, we know that's a reflection over the x-axis, which means the left side is up and the right side is down. The way we write this, okay, left, down, right, up, or left, up, right, down, that's not how we write it. The notation is the tricky part. So we are going to write it in limit notation. So the limit as x approaches negative infinity of our function f of x. Notice that the limit part is written kind of like a fraction without the fraction bar. The x arrow number is right below limit. And then we put our function normal size next to it. This is saying as x gets closer and closer to negative infinity. Well, negative infinity is way, way, way to the left on a graph. So basically I'm saying, what's the left side doing? Well, the left side is going down forever. Down forever means my y value is approaching negative infinity also. For the right side, we say the limit as x approaches positive infinity of our function. That's just how we say the right side. Well, in this function, the right side goes up forever, which means it is going up to positive infinity. If the leading coefficient is negative, we switch those. So the limit as x approaches negative infinity, remember this is saying the left side. If it goes up forever, then it's infinity. And the limit as x approaches positive infinity of f of x, that just means the right side, well, it's going down, so that is negative infinity. Even degree functions are a little different. Even degrees, if you think about your basic parabola, the leading coefficient's positive, it opens upward, right? Does whatever it wants in here. Both ends go up. So that means the left goes up and the right goes up. If the leading coefficient is negative, on the other hand, it goes down and down. So left, down, right, down. That's the simple way to say it, but with our math symbols, for the left side, we say the limit as x approaches negative infinity of our function. Since it goes up, that is positive infinity. And the right side is the limit as x approaches infinity of our function. It goes up, so that's infinity. For the negative leading coefficient, the left side, the limit as x approaches negative infinity. It goes down, so that's negative infinity. And the right side is the limit as x approaches positive infinity. It goes down, so that is also negative infinity. So the limit notation is new. These tests, very straightforward, leading coefficient and and degree. So some pictures here, pictures that I didn't draw, so they're probably better. So as x moves without bound to the left or to the right, meaning it approaches negative or positive infinity, the graph of the polynomial function eventually rises or falls in the following manner. If our degree is odd, the left side goes down, the right side goes up. If it's positive, and if the leading coefficient is negative, the left side goes up, the right side goes down. When your degree is even, if your leading coefficient is positive, both sides go up. If it's negative, both sides go down. The dashed portions are just because the test only tells us anything about the ends. It tells us nothing about the middle. We'll talk about the middle more, don't worry. So let's use the leading coefficient test to determine the behavior of these functions. So the first thing we look at is the degree. The degree of this function is 3, that is the biggest exponent. The leading coefficient is -1. We only care if positive or negative. It's negative. The degree 3, remember, is an odd number. So it's an odd function with a negative leading coefficient. That means the left side goes up, does something, the right side goes down. So we say the limit as x approaches negative infinity of our function is up, so it's positive infinity. And the limit as x approaches positive infinity of our function goes down, so it's negative infinity. For number 2 here, our degree is 4, so that's even. Our leading coefficient, there's nothing there, which means it's 1, which means it's positive. Even with a positive means both ends go up, and it'll do whatever it wants in the middle here. So we write the limit as x approaches negative infinity of h of x, because that's the name of this function, is infinity, since it goes up, and the limit as x approaches infinity of h of x also goes up, so it's infinity. And g of x equals x to the 5th power minus x. Well, our degree is 5, which means it is odd. Our leading coefficient is again 1, which means it's positive. Odd with a positive goes down on the left, up on the right. So the limit as x approaches negative infinity of g of x, left side goes down, so negative infinity. And the limit as x approaches infinity of g of x is infinity because the right side goes up. So, important note, the leading coefficient test tells us the end behavior, but nothing about the inside, okay? Nothing. We don't know if it crosses the x-axis or where, how many times it turns, none of that from the leading coefficient test. But zeros can help us with some of that. So for a polynomial function, f of degree n, the graph has at most n real zeros. So the number of zeros can be at most the degree of the function. And it has at most n minus 1 relative extrema, maxes or mins. So if my degree is 7, I could have 7 zeros, I could have 6 maxes or mins. Remember that zeros are the values of x when f of x is equal to 0, when your y value is 0. And all of these are the same. X equals a is a 0 of the function. X equals a is a solution of the equation f of x equals 0. X minus a is a factor of the polynomial. And a comma 0 is an x-intercept of the graph. All of those mean the same thing, just stated slightly differently. So let's find all the real zeros. If I look at this function, I see the degree is 3. I know there could be at most 3 real zeros. We find the zeros by changing f of x to 0 and factoring. I'll take out my GCF, which is an x, first. I get x squared minus x minus 2. Well, can I factor that? I sure can. X minus 2 times x plus 1. Then I set each of those equal to 0. Each factor. I solve. I have x equals 0. I add my 2, so I get x equals 2. And I subtract my 1, so I get x equals negative 1. I have 3 real zeros. For B, I see my degree is 4, so I could have at most 4 real zeros. Start the same way, set it equal to 0, take out my GCF. I'm going to take out negative 2x squared. That leaves me x squared minus 1. Well, x squared minus 1 can factor into x plus 1 times x minus 1. And then I set each factor equal to 0. For the first one, I divide by negative 2, giving me x squared still equals 0. And then I square root, giving me x equals positive or negative 0, which is just 0. Subtract 1, I get x equals negative 1. Add 1, I get x equals positive 1. I only had 3 real zeros on this one. Remember, I can have at most 4 because that's the degree, but you can always have less also. Sometimes we have less because of repeated zeros. So a factor, x minus a to the k power, if k is bigger than 1, yields a repeated 0 at x equals a with a multiplicity of k. So multiplicity is how many times that is a factor. If the multiplicity is odd, we're going to cross the x-axis at that value. If the multiplicity is even, we touch the x-axis but don't quite cross. So it's important to realize the graph of a polynomial function can only change signs at its zeros. So it can only switch between being negative y values and positive y values at a 0. Between the zeros, it's only going to be positive or only negative. So the 0, when put in order, will divide our graph into test intervals that can help us when we graph. So let's find our zeros, multiplicities, and state if they're touch or cross points. First one's pretty straightforward. It's already factored for us. So to find my zeros, I set each factor equal to 0. Well, if I set negative 3/5 equal to 0, I don't get anything. If I set x plus 3 equal to 0, I get x equals negative 3. And if I set 5x minus 1 equal to 0, I add my 1, and then I divide by 5, giving me x equals 1/5. So my zeros are x equals negative 3 and x equals 1/5. But then we have to say their multiplicities. Their multiplicities are these exponents. X plus 3 gave me negative 3. It has an exponent of 4, so the multiplicity is 4. 5x minus 1 gave me the 1/5. It has an exponent of 5, so the multiplicity is 5. That determines touch or cross. Ooh, sorry, my light's very bad. If the multiplicity is even, it touches. If the multiplicity is odd, it crosses. So that means my graph touches the x-axis at negative 3, but doesn't quite cross. It does cross at 1/5. All right, let's use a different color because that one's not a fan. This next one, to find our zeros, we're going to have to factor. We have 4 terms, so my go-to would be factor by grouping. Take out the GCF from my first 2 terms. It is 4x squared, leaving me x minus 1. Take out my GCF from the last 2 terms. It's negative 25, leaving me x minus 1. So that means it factors into x minus 1 times 4x squared minus 25. Well, 4x squared minus 25, those are both perfect squares, so I can make it 2x plus 5 times 2x minus 5. It is fully factored, so I can quickly get my zeros now. X minus 1 equals 0, gives me x equals 1. The exponent on that was 1, so it's got a multiplicity of 1, and that means it is a cross point on the x-axis. If I set 2x plus 5 equal to 0, subtract my 5, I get 2x equals negative 5. Divide by 2. I get x equals negative 5 over 2. The exponent on that factor was a 1. Remember, an invisible 1. So it's got a multiplicity of 1, which means it is another cross point. And 2x minus 5 equals 0. We add the 5, giving me 2x equals 5. Divide by 2, giving me x equals positive 5 over 2 for my last 0. The multiplicity again is 1. And it is a cross point. There's our 3 zeros. All right, let's factor, find our zeros, tell if they're touch or cross points. First thing I see here is a GCF. I'm going to take out an x. Leaves me x squared plus 10x plus 25. Well, that's going to factor into x plus 5 times x plus 5, which can be rewritten as x times x plus 5 squared. So my first 0 is the x. It had an exponent of 1, so it's got a multiplicity of 1, which means it is a cross point of my graph. Then I said x plus 5 equal to 0. I get x equals negative 5. It's got a multiplicity of 2, since the 2 is the exponent, which means that is a touch point, not a cross point. Next up, we have 2x to the 6th power minus 14x to the 4th power. I can have at most 6 real zeros. When I take out my GCF, though, 2x to the 4th power, I'm left with x squared minus 7. All right, well, when I set this equal to 0, x to the 4th power gives me just x equals 0 with a multiplicity of 4. So that's a touch point. X squared minus 7. We can't factor that, but we can solve it by setting it equal to 0. I add the 7 over, I get x squared equals 7. I square root and I get 2 answers. X equals the square root of 7 and x equals negative square root of 7. Each of those only have a multiplicity of 1 because together they make the x squared. And that means they are both cross points of our graph. So when I say real zeros, they don't have to be rational. Square root of 7 is a real number, just not rational. All right, let's talk about intermediate value theorem. So if f is a polynomial function and a is less than b, if f of a and f of b have opposite signs, then f has at least one zero in the interval a to b. So basically, if f of a is positive and f of b is negative, we had to cross the x-axis in between them. Or vice versa, if f of a is negative and f of b is positive, again, we had to cross the x-axis. So let's show that there must be a zero in this interval. To show that, we have a couple very simple steps. We will find f of negative 4, and we will find f of negative 3. Okay, those two values that are in that interval. And for this, I will grab my calculator. Make sure I can see everything. All right, I want negative 4 to the 4th power plus 6 times negative 4 to the 3rd power minus 26 times negative 4 plus 15. I got negative 9. All right. Then I'll do the same thing with negative 3. Work smarter, not harder, right? Just go back through, change all those negative 4s to negative 3s. I got positive 12. Now comes the precalculus part. One of these is negative, one of them is positive. That means there is a 0. So f of negative 4 equals negative 9, which is less than 0, which is also less than my other value of 12, which is f of negative 3. So there is a 0 on negative 4 to negative 3. Somewhere between negative 4 and negative 3, it crosses the x-axis. You could use this for any value. I could say that there's also a value where it hits 7, because that's between these two numbers. It works. And finally, we are going to talk about how to put all this together into sketching a graph. So let's start with our end behavior. Our degree is even. Our leading coefficient is positive. So the left side, the limit as x approaches negative infinity, goes up, so it's infinity. And the right side, since it's even degree, also goes up. There's our end behavior. Find our zeros. Factor out my GCF, which is x cubed. Leaves me 3x minus 4. So x equals 0 has a multiplicity of 3, which means it crosses. And then the other one will be positive 4 over 3 with a multiplicity of 1, which means it also crosses the x-axis there. All right. Sketch my little graph here. I'm going to cross at 0 and 4/3, so we'll go like that. Now this does not tell me anything else. I know the ends both go up. I know I cross the x-axis here and about here. For right now, we can start from up. We cross, go down something, cross. Sure, something like that. Technically speaking, though, the higher the multiplicity, the more it's going to kind of wiggle there, for lack of a better word. So really, as we come down to 0, we're going to do something like that, and then go back up like this, because the multiplicity is 3. So better graph would be that one with the kind of squiggle there. All right, then this is your assignment to work on all these things.